Okay, we're going to see this solution for part A3 of project number 2, the one that I implemented. I'm pretending I was a student doing that thing. I did start this from scratch using the same program that I gave you at the very beginning, and I was adding things for all the project that we were solving. Good. So I will show here my main page, my figure. The only thing that I'm not including here is a good bias. I'm putting here now 1.2 degrees per second bias. I already implement this version of the localizer considering the bias in the estimation process in the state vector. And I also assume that could be between minus plus 2 degrees per second, assuming that that was the type of sensor having that range of possible value for the bias. And then I will run this thing. The rest of the settings are similar to the one that you have. Yes. Yes, I could suppose I'm pretending I'm changing those things. Good. And then I run this thing. And with this bias, you expect that this is going to behave not good, but it's going to do okay. Yes, doing all right. I'm going to be running. I think at this moment it's already learning well the bias. I put a lot of bias. That is a terrible bias. You wouldn't like to buy a gyroscope having such a bias. And then we keep running. It's going to finish soon. It's estimating the bias, and it's plotting here. Producing the outputs, certain other figures that are not there. Here are the one that we had discrepancy or consistency plot for X, Y, and phi. And I also had the ones which correspond the plot of the estimate. Here, I put this here. That was the tuning during the run. I should put this here, the same like this one. Yeah. This is what was happening with the others. I'm going to reduce the size of this. Yeah. That was the evolution. That was the error, discrepancy, X and Y, and also in the heading. And I also showing here how was the first and one standard deviation, two standard deviation. It was, but also simultaneously we were estimating the bias, and I think I include 1.2 degrees, and now I forgot. So initially we have 0. Initially it's doing nothing. It's not learning. Why is that? That's not because the machine was not moving. You remember during the first fraction of, I don't know, few seconds, fraction of time, the machine is not moving, and there is no way for our system to learn the bias. But as soon as it starts to move, the system is getting observable. And then you see that they have this sort of overshoot negative. And after that, start to catch up very soon. And it's trying to 1.2, and finally it's learning, and finally got something which is very close to the real bias. These are very small values. We are very happy with this because it's very close to the bias. If we don't consider a bias which is about 1 degree per second, or even more in this case, in magnitude, that is a terrible problem in our kinematic model, because in 10 seconds you will be 10 degrees off. Your estimate will be telling you that the heading is 10 degrees different to the actual one, and that is a catastrophic issue. So we are in condition to estimate this thing. And if the bias was 1.2, having this small discrepancy, 0.01, that is not an issue for us, because the rest of the estimation process, applying correction through the Kalman filter update, is going to deal with that. So we could deal with a small bias. We cannot deal with a large bias. So we need to learn that bias. We need to tune that parameter. And this is what it was doing, our part A3 in our project. Magically, you say it's doing that thing. Yes, because the system is observable. And I'm just applying what we discussed in the previous part of the video, in the first component of the lecture, in which I was mentioning how to augment the state vector, how to modify the prediction step, and how to adapt the update step for dealing with this extra parameter in our state vector. And this is the story. Everything is here. It's working well. So I expect that you will be in condition to solve that.